Hello, welcome back. To wrap things up, I'd just like to do a few more quick examples illustrating this describing function harmonic balance method for predicting limit cycles. So we're just going to focus in on exactly the same situation that we've had so far. So we have a linear system G in feedback with a static nonlinearity H. We've got negative feedback, and we're going to look at some setups where we have our two favorite static nonlinearities, the relay and the saturation. And here, just for simplicity, we've got the limits at 1 and -1 for our relay, and our saturation is all ones. So we've got these two static nonlinearities. We've seen how to calculate their describing functions, and now we just want to get a bit of practice using the method of harmonic balance to predict whether we get limit cycles, and also if they're going to be stable or unstable. So we'll just start with kind of a simple one that's pretty closely related to what we saw before. So we're going to look at G is equal to 1 over s plus 1 cubed. And what can we say about this transfer function? Well, it's stable, first of all. It's got all of its poles in the left half plane. And how about its Nyquist diagram? That's what we need to draw. Well, if we put in s is equal to j omega and omega equal to 0, so we look at G of J0, well, the size is just 1. As we send omega to infinity, we come into the origin, and we come in at an angle of -270 degrees, and that's because the denominator's got a cube in it, and we've got nothing in the numerator. And if we were going to do this properly, we would go and put in a few more points and build up our Nyquist diagram. Once you've done these things a few times, you just know that the Nyquist diagram in this case looks something like that. So this is 0 frequency. This is infinite frequency. We've got this linear system. Do we predict a limit cycle or not? So the key thing we have to look for is our condition of harmonic balance. So we're looking for the condition G of j omega is equal to -1 over n of A. And the way we look for limit cycles with this method is we now plot on our describing function diagram. And just as we saw last time, that just means that we plot on -1 over n of A for different values of A, and we build a curve in exactly the same way that we build a Nyquist diagram curve by sweeping over frequency. And so if we start by analyzing this particular G in feedback with our relay, we have to draw on the -1 over n of A curve, and if we put A is equal to 0, -1 over n of A is equal to 0. And then, as we saw before, as we make A bigger and bigger and bigger, -1 over n of A just becomes more and more negative, but it stays real. So this is what the -1 over n of A curve looks like. This is what it looks like for the relay nonlinearity. So do we predict any limit cycles? Yes, we have an intersection between our Nyquist curve and our describing function curve, and so we predict a limit cycle with the frequency of intersection. So we get the frequency from the Nyquist curve, and we get the amplitude from the describing function curve. So maybe we should build like a little table here. So limit cycle, question mark. Yes. And do we predict a stable limit cycle? Well, as we explained last time, the way we do this is we look at amplitudes either side of the point of intersection, and then we say, okay, well, imagine this was our -1 over k point. do we predict closed loop stability using the Nyquist criterion? And what we want is, for small a's, we want to predict instability, and for large a's, we want to predict stability, because that means that if we start with the small value of a, we're unstable, so we get the signals get larger, they get pushed through, and then we enter the region of stable A, and we get pushed back, and we just sort of oscillate backwards and forwards, and we'll settle onto this limit cycle. Yeah, this is the world of describing functions, so it's a heuristic method, but this is a pretty good indicator of whether or not we expect to get a limit cycle or not. So what happens in this case? Well, our transfer function g is stable. So g is stable, so the system is open loop stable, and so by the Nyquist stability criterion, we need there to be 0 encirclements of the -1/k point for the closed loop to be stable. So if we're on this point, so if we're on this a value of small a, we have an encirclement, and so we predict instability by the Nyquist criterion, which means a will grow. And similarly, for large a, we get no encirclement, so we predict stability by the Nyquist criterion, so a will decay. So yes, plus it's stable. And if you were doing this in an exam or something, you'd have to talk through the reasoning I just gave you now, but that's what you would need to say. So that's fine. How about if we look at this other describing function here? Well, we've not really examined much of what this would look like, so let's just draw a little picture down here. So let's draw a on this axis, and what does n of a look like? Well, for values of a less than 1, n of a is just equal to 1. So it's flat, something like that. And then what happens when a gets very, very large? Well, when a gets very, very large, this term here, this is just equal to 0. We've got a 1/a, so this all goes to 0. And similarly, sine to the -1 of 0 is just 0. Sine cuts through the origin. So as a gets very, very large, n of a goes to 0, and actually it just sort of connects up in some sort of smooth manner there. So you get a little kink at the point where we switch from this relationship to this relationship, and it's continuous, and then as a gets bigger and bigger, it gets smaller and smaller and smaller. So what does -1/n of a look like this time? Well, when a is equal to 0, n of a is equal to 1, so -1/1 is just -1. So now our -1/n of a curve, it starts here, and then as a gets bigger and bigger and bigger, n of a gets smaller and smaller and smaller. So 1/n of a gets bigger and bigger and bigger and bigger, and so it goes this way. So what do we get? Well, do we get any intersections between our -1/n of a curve and this guy? No. So we don't predict any limit cycles, and that's the end of that, really. Okay, good. So that was simple enough. Let's just do one more example to hammer home these ideas. Let's do an unstable case because they're a bit more complicated. So we draw another picture of the complex plane. Yeah, this was the complex plane too. Why don't we shove that on? And let's now look at the transfer function. G is equal to e to the minus st all over s minus 1. So now we've got a pole at 1. So this is an unstable system. We've got a delay in here. Let's make this 2. So what's going to happen? So again, the first thing we need to do is plot our Nyquist diagram. If we put omega is equal to 0, it's just equal to -2. And then we know whenever we have a delay, so this is going into it's decaying into the origin as omega gets very, very big, the denominator gets very, very large. But we get this sort of spiraling effect whenever we have a delay. And in fact, we get a curve that looks something like that. So this is our Nyquist diagram. This time, here's omega is equal to 0. Here's omega is equal to infinity. And maybe you would go and plot a few extra points to try and get a more accurate representation of this curve. So this is the Nyquist diagram. Let's go and do some describing function analysis. So just as before, we draw on our describing functions, we look for intersections, and then we analyze the limit cycles that we predict. So let's start with our relay again. Now things are about to get a little bit busy here. So whenever you have unstable systems, the Nyquist criterion gets a little bit more complicated to apply. It's not so easy to just infer the encirclements just by looking at the Nyquist diagram. You actually have to complete the Nyquist diagram, and to complete the Nyquist diagram you actually have to plot on the values for negative frequencies. And to do that, we just take the picture that we have already and we mirror it in the real axis. So the full Nyquist diagram actually looks something like that, and the curve is going that way. So now things get a little bit easier to count encirclements. Let's go ahead and try and predict some limit cycles. Well, yeah, looks like we're predicting a few limit cycles this time. So we've got one crossing here. So this is a potential candidate for harmonic balance. This would be a bit of a weird one. You can maybe already begin to see that this is the point corresponding to omega is equal to 0. That's not much of a limit cycle. Remember, our limit cycle is of the form a sine omega t. And with omega equal to 0, there's not a lot of oscillation happening, but we've got an intersection, and maybe that will tell us something. We've got another intersection here, and actually we've got loads and loads of intersections here. I'm not going to talk about these. Maybe you can go away for yourself and explain why any limit cycle in here will be predicted to be unstable when we apply the Nyquist type argument. It's just a bit... I would have to redraw things to be able to really see what's going on, and maybe it's a good exercise in applying the Nyquist criterion. So we're just going to look at these two candidates here. So yes, it looks like we've got two potential limit cycles. Are they stable or not? So what happens? So we have to do exactly the same thing. Let's do case 1 first, and then let's say this one here. This is our case 1. Now, counting encirclements gets a little bit harder, but there's a nice trick that will always help us to resolve things. So it's not so important to use it this time. Actually, you can sort of eyeball it anyway. But the method is exactly the same thing, same as before. So we take a smaller value of A, and we see, is it unstable? And then we take a larger value of A and see, is it stable? And if that's the case, we're predicting a limit cycle. So let's do that here. We take the smaller value of A, and how many encirclements do we have? Well, we have 1, and it's actually clockwise. You can see the curve is cutting around in a clockwise manner. If you want a really robust way to make sure you always count correctly, just take a point. So we want to count encirclements at this point, and just draw a straight line. Doesn't matter what direction you draw the straight line in. Let's draw it that way. And then we just look at the number, the senses of the cuttings of that line. So this curve has cut through this line once in the clockwise direction, and therefore we have 1 clockwise encirclement to this point. And this method will always work. So what does that tell us? Well, we have 1 unstable pole. Therefore, by the Nyquist criterion, the closed loop is stable if and only if we have 1 anti-clockwise encirclement of the -1/k point. We have 1 clockwise encirclement. So this is unstable. So small a is unstable. That's good for limit cycles. How about large a? Well, maybe you can already see. if we do the same thing, we take our point, we draw any old line out, now we see that we're getting one clockwise cutting of our one anti-clockwise cutting of our line. So we have one anti-clockwise encirclement. So large A is stable, small a is unstable. So case 1, stable. Let's do case 2 now. We've already sort of indicated that even if we concluded stability, it wouldn't make a lot of sense because this is omega is equal to 0. But we can maybe kind of guess that we're already in trouble. Small a, we know is stable because it's the same as when we counted over here. And now large a is unstable. So this is the bad situation. If the amplitude is too small, it'll just decay away, and actually it'll settle into this limit cycle. If the amplitude is too large, it'll just wander off. So unstable, but also not really a limit cycle. Anyway, and now you can use the same method to try and deduce that all of these must be unstable too. And we'll just round off. You can probably already see where this is going. If we now draw on the describing function for our saturation, what is going to happen? Well, again, -1 is here. And so we go something like that. We predict one limit cycle. Again, it's the fake one with omega is equal to 0, but it's predicted to be unstable anyway. And you see something slightly interesting going on here. So if the delay, as the delay gets bigger, this curve starts happening earlier and earlier. And so maybe for certain values of the delay, you will start to predict a stable limit cycle even when using the saturation. So yeah, let's just write this. So yes, and unstable. Fine. And that sort of concludes things as far as our describing function analysis goes. I just want to finish with some concluding remarks about the case with relays. So as we've seen, the describing function of a relay covers the entire negative real axis. And it's very, very common for transfer functions to cut through, that have Nyquist diagrams that cut through the negative real axis. And we've seen 2 examples already, but pretty much wherever this happens, you start to get stable limit cycles. So relays are great causers of limit cycles, and in fact so much so that this property is often actually exploited in methods for control system design. And the really useful thing here is it gives you a method for identifying properties of systems that you don't know. So now let's suppose that we have a transfer function g, we don't know what it is, but we connect it in feedback with a relay. And now when we take some measurements in our system, we start to observe a limit cycle appearing. And the limit cycle has got a particular amplitude and a particular frequency. And if you think about it, what that's telling us, we know the describing function of the relay, so the relay part of this picture is known. What this ends up telling us is this ends up telling us that the Nyquist diagram of the system, we don't know what it is, but it must cross through the negative real axis at this one point here. And so by putting this relay in feedback with this system that we don't know, we're able to identify one point on the Nyquist plot. But this is a very important point. This is a point that's near the -1 point. So you can actually already start to go and design proportional controllers or PI controllers to try to stabilize things or improve the behavior of this unknown system. And the way that you come up with the tunings for those proportional or PI controllers is based just on knowledge of that single point on the Nyquist diagram. It's a very clever method and is very widely used in industry, particularly in methods for automatically tuning PI controllers in processes that are maybe changing over time. So you don't have, there's not a fixed model of the process. It's changing depending on weather or wear and tear of the equipment or whatever. And you don't want to go in and do a detailed identification every time. So instead, you slam in a relay, you observe a limit cycle. This gives you a single point on your Nyquist diagram, and that's enough to go and design your controllers. And it's very widely used, and it was developed here in Lund. So there's a little bonus for you on describing functions and limit cycles to round things off.